Okay, going to do a screencast with to go over a few of the multiple choice questions that were asked about this morning that we didn't get to, and one of the free response questions on Form A. So the multiple choice questions that you guys asked about were 5, 6, 12, and 15, and also the last free response question on Form A. So I'm going to start with number 5 here. And it mentions a stationary object. So it starts out with no momentum, explodes, breaking into 3 pieces that have these masses. 2 of the pieces of mass m move off as shown here at right angles to each other with the same magnitude of momentum but in different directions as shown. And they ask what's the magnitude and direction of the velocity of the 3rd piece that has a mass of 3m. So you've got to find the velocity and direction of the 3rd piece. So these 3 pieces together were at rest beforehand. So the sum of the momenta after the explosion has to be 0. So if you look at the first 2 vectors here, the mv to the right along the x-axis here and the mv vertically up, combined they have a momenta that looks like this. And if you think of a 45, 45, 90 triangle, it's basically, I drew that a little bit too long. Still too long. Wow, not very good. So this is going to be square root of 2 mv. Just a 45, 45, 90 triangle. This is 1, 1, square root of 2 times mv. So the magnitude of that hypotenuse is square root of 2 mv. So the amount of momentum of the last piece, the final momentum of the last piece, has to be such that it offsets that momentum, because the final momentum of the 3 pieces together has to add up to 0, because the initial momentum was 0. So basically square root of 2 mv plus momentum of the 3m piece has to be 0. So it has to be in the opposite direction. So the magnitude of this piece, magnitude of the momentum of this piece, let's say P3, is going to be equal to this, but in the direction down to the left. So let me move this over here. This is going to be the direction. So that immediately eliminates all A and D as options. A and D, it eliminates A and C as options. So those are out because they have the wrong direction. Okay? So back to this, I know the magnitude of this momentum has to be square root of 2 mv to offset the first 2 pieces. So the momentum of piece 3 is the mass of piece 3, which is 3m, times the final velocity of piece 3 has to be equal to square root of 2 mv. Solve for the final velocity, you're going to get root 2 over 3v. The m's cancel out. So the final velocity will be root 2 over 3 times the velocity of the first 2 pieces in the direction down to the left. So that was option D right there. That's the right one. Okay, let's look at number 6. Somebody asked about. Number 6 is a little different. It asks about impulse. A net force is applied to a block of mass 4 kilograms, and the force time graph is shown above. The impulse given to the mass between 0 and 0.12 seconds is most nearly, and they give you some options here. To calculate the impulse between 0 and 0.12 seconds, it's going to be the area under this graph right here. So the area under that graph is impulse. And you've got force versus time. It's a triangle shape. You know the base is 0.06. So the base is 0.08 minus 0.0602 seconds, sorry. So the base is 0.06. The height is 800, so 800 newtons. So the impulse, F times delta t, which is, that's J, is the impulse. That is 800 times 0.06. That is 48, but it's 1/2 base times height. I forgot to put my 1/2 in there. That is 24 Newton seconds. Because it's a triangle, obviously, half base times height. 24 Newton seconds, and it is in the positive direction. All these answers were positive, actually, so the correct answer was A. Number 12 is the next one that people asked about. So let's go to number 12, top of this page right here. Rubber ball is held motionless at height h0 above a hard floor and released. Assuming that the collision with the floor is elastic, that's very important because elastic means no lost kinetic energy. So whatever kinetic energy it had before the impact of the floor, it has the same kinetic energy after the impact of the floor. What's a relationship between the total energy of the ball and its height above the surface? Well, if you can picture dropping the ball from a height, comes down, hits the floor, does not lose any kinetic energy, so it bounces back up to the same height it came before because it's going to have the same energy and the same velocity there as the velocity it had just before impact. So it's going to bounce up to the same height. The fact that it asks for total energy includes gravitational potential energy. So you've lost no energy whatsoever. The energy stays constant over the entire trip. So that's part A, or that answer is A. Okay? Number 15 was the next one. Two objects having the same mass travel toward each other on a flat surface, each with a speed of 1 meter per second. So they're on a flat surface. The objects collide head-on and are reported to rebound after the collision, and each one has sped up. So if you figured kinetic energy on this before and after, there's actually more kinetic energy in the system after than before. Momentum is conserved, surprisingly, because you had zero momentum before the collision, you have zero momentum after the collision. Before the collision, these two things are coming at each other with the same velocity of 1 meter per second. And afterwards, they're departing from each other with an equal velocity of 2 meters per second, okay? 2 and 2. So opposite directions, same velocity, same masses. In both cases, momentum is 0. The issue is that energy has been gained. And so you're trying to figure out where did that energy come from. If potential energy was released during the collision, the report could be true. That means that if they were those little, if they had some kind of spring that was tripped, maybe some elastic energy was stored, and perhaps it tripped a spring and those two things got pushed apart with a greater velocity, that would be potential energy that was released, and perhaps they would have actually sped up because you've got some new energy added to the systems. The objects having different masses does not account for an increase in kinetic energy. If the surface was inclined, that doesn't account for an increase in kinetic energy. One of them may have gained energy on the way out because it was going downhill, but the other one would be going uphill after the collision. And again, when you talk about the duration of this collision, it's a very, very short time frame. So you're talking about milliseconds for most collisions. So the effect of that uphill-downhill is not going to be super great, although it will have a little effect. It would not be that great, and it would have opposite effects on the two objects, so they wouldn't both gain velocity anyway. Okay, so that hopefully helps you understand why the A, C, and D were not correct options on that one. Now I'm going to do the last question on A. That was this one right here. Had a small block of mass M released from the top of a curved frictionless ramp. So here's this block, it's released from the top of the ramp, and the block slides down the ramp and is moving with a speed of 3.5 V0. We don't know what V0 is, but it's 3.5 times that speed when it gets down here to the bottom. And it collides with a larger block of mass 1.5 M. So that block is 1.5 times more massive than the one at the top. And it's at rest. The larger block moves to the right at a speed of 2 V0 after the impact. So it's going to move this way after the impact. And we want to figure out our answers to all these problems in terms of the given quantities. Again, I have to stress to you guys, it's very important you use the nomenclature and the symbols that were given in the problem. So don't use just V. Any V's in your answer have to have a zero, V0, a capital M for mass. You can't invent your own variables and expect the reader or the grader or the test to be able to understand what you meant by it, okay? So now we're trying to determine the height of the ramp from which a small block was released. So on this one, here I've got this block of at 3.5 V0. This is the block here, has this speed when it gets to the bottom. So I have to figure out from what height that block was released. This should seem to you like a good opportunity to apply conservation of energy, because I've got a change in height, and I've got up here, I've got all UG in my pi up here, and I've got all kinetic energy, translation of kinetic energy here. Nothing's rotating. So I've got UG equals K, so mgh equals 1/2 mv squared. We know what this final velocity is. It's 3.5. I have to substitute in my variables now, but my m's are going to cancel out. So my initial height is going to be 1/2 3.5 V0 quantity squared divided by G. So if you put some numbers in this, it's always good to simplify. What I got when I simplified is I got 12.25 V0 squared over 2G, which is the same as 6.125 V0 squared G. G can be in your answer. You do not need to put 10 in there and reduce this to 0.6125. If you want to, you can. You don't have to. You can leave it just like that. So there's the height in terms of V0. So we answered in terms of the given quantities and the fundamental constants. That's G. So go ahead and leave G in your answer. Part B, determine the speed of the small block after the collision. We have enough information after the collision. We know the mass and the velocity, the mass and the velocity of the larger block. And we know the mass and initial velocity of the small block that comes in contact with the large block. And so all we need to do is use conservation momentum for that impact to find the final velocity of the small block. Now, I don't remember if it says that they are, if they stick together. It does not say they stick together. It does not imply that they stick together. So we are going to go ahead and assume they don't. Okay, so we've got part B, conservation of momentum. Start your problem out with a conservation momentum statement. That might be worth a point right there. The reader now knows that you're using the big idea of conservation of momentum to solve this problem. The initial momentum would be m 3.5 V0 for block, is it block A? They don't have A and B here, just block M. Okay, and at the end, I've got that mass times Vf plus block 1.5 M times its velocity of 2 V0. So it's just a matter of simplifying this. So I've got all my M's here are going to cancel out. All the terms have M in them. So 3.5 V0 equals Vf plus, looks like 3 V0, 1.5 times 2 is going to give me 3 V0. I subtract 3 V0 from both sides, and I get 0.5 V0. So that small block is going to have a velocity of 0.5 V0 after the collision. So that's the speed of the small block after the collision in terms of the given quantities again, which are, which is the V0. So I have to have that in my answer. The larger block slides a distance d before coming to rest. Determine the value of the coefficient of kinetic friction mu between the larger block and the surface on which it slides. So a distance d before coming to rest. You could actually use kinematics to solve this. I'm going to, actually, I'll stay on that page. I'm going to not use kinematics. I'm going to use conservation of energy. And if you think about the type of energy that I've got at the beginning, after these two blocks collide, these two blocks are going to collide. And after they collide, they're going to travel a distance d. Actually, no, just the one block, sorry. We're focused on just the larger block, sorry. The 1.5 m block is going to slide distance d. So it has no energy at the end. It had some kinetic energy at the beginning of the sliding process. So you're looking at the problem now just from the point of time after the impact, when it's got a velocity of 2v0 to the point at which it stops. That's the duration of this part of the problem. So all that kinetic energy I had at the beginning, right after the impact, is gone by the end. Where did it go? It went into work done by friction. Okay, so we can figure that out using conservation of energy. And we can say, for part C, you can say all that kinetic energy initially went into work done by friction. Well, how about if I write it this way? Into U thermal, which is the work done by friction. So that 1/2 mv squared is going to be the friction force times d. And I'll write my friction force like that. Okay? And remember what friction is. Friction is mu times the normal force. Okay, I'll just use an m for the normal force, which is mu times mg since we're on a flat surface. The normal force is going to be equal to the weight of the object. There's no vertical forces to add or reduce the normal force, increase or decrease the normal force. So umg is my force of friction. That's going to go over here. My initial velocity of 1.5 m block is 2v0, and my mass is 1.5 m. So I have 2v0 quantity squared equals mu mg times d. We're trying to solve for d in terms of all these other variables. I can eliminate m. I've got 2 squared is 4, times 1.5 is 6, divided by 2 is 3v0 squared over here, and I'm going to divide by mu g. Something's not right about that. What did I do wrong? Let's check this out here. 1.5 m. Oh, I know why. Sorry about that. Because this is also 1.5. This is 1.5 capital M. So this is 1.5 capital M, G, and then I'll put the mu in front of all that. Okay, so this whole thing is going to cancel out. So I'm going to have 2 over here. And that's my final answer. 2v0 squared mu g. I mentioned there was another way to do this with kinematics. You could have used, found the acceleration using vf squared equals v0 squared plus 2a delta y. This is d. Final velocity is 0. So you would have gotten an acceleration from that. And then using F equals ma, and the only force was your friction force, mu mg, because the force diagram on that object was mg, normal force, and the unbalanced force is the force of friction opposing the motion. So you could have done it this way. A couple people actually did do this and set mu mg equal to ma, found a from this equation right here in terms of d, and then using Newton's second law and the kinematic equation, got exactly the same answer. So there's always, not always, many times more than one way to solve the problem. So if you got it using energy, totally fine. If you got it using kinematics, that's good too. Okay? So if you have any other questions, please feel free to come see me. We'll go over them. And before or after school or during a free period, 8 hours, fine too. And I will see you tomorrow.